Welcome to my YouTube channel. In this video, I'll show you how to analyze simultaneous equations using operational amplifiers. Now, so as to avoid clumsiness of diagrams, I've decided to use this symbol here. This symbol is equivalent to this circuit, this inverter circuit, whereby this part here called the summing point is just this part over here, these branches. And also I'm going to use this symbol over here. Note that it has a bar, so this symbol, it will be used in place of this circuit to mean inverting integrator, whereby these branches form the summing point, like in this circuit. Now we are provided with these two sets of equation, our equation 1 and our equation 2, and what is expected from us from the equation, we have to draw an open loop and a closed loop flow diagrams of these two equations. For us to achieve that, we'll have to follow a series of procedure. First, we're going to have a set of two equations, of which we have equation 1 and equation 2. Then we're going to treat the two equations as separate. Also, one variable will be made the subject in one of the equations. Then we are going to obtain what we call a potentiometer. I'll show you how to do that. Then we are going to make a circuit diagram for each equation, for our equation 1 and our equation 2, of which it will be an open loop. Then we are going to combine the two blocks to make the block diagrams. Now I'm going to start with our equation 1, since in the procedure it says treat two equations as separate, that is, work one equation at a time. Now here I'm going to introduce dot method to represent different orders of these differential equations over here. So our x will have two dots to denote it is a second order differential equation. The same it is for y, since it is a second order, and our x with one dot to denote that it is first order differential equation. Now then we are going to make one variable the subject of the formula. So we usually choose the variable with the highest order, for example our x, okay, and then we make it the subject of the formula. Now we'll obtain this equation. That is after doing everything that is here backward. Note that the sign will change. Then our fourth procedure is saying we're going to obtain the potentiometer. Now first, before we apply what is called potentiometer, it is very important to introduce a negative sign. So we'll introduce negative sign at the whole equation. So by introducing a negative sign, everything here will change. If it was a negative, it will change to a positive, and if it was a positive, it will change into a negative. Then something important to note, for potentiometer, we deal with the gain that does not exceed unity, okay, that is less than unity. So if we look at these factors here, our 3, our 4, and our 10, and our 2, we cannot say it is a gain, okay. So what it suggests is that we are going to adjust this value here to be less than unity, and we can achieve that by doing this, whereby 10 times 0.3, it will get us back here. Note that 0.3, it is less than unity. Okay, the same applies for 4 and for 10, whereby we'll have to multiply 100 by 0.01. Okay, for this 0.1 to be in unity, less than unity. Then also it will also apply to our 2 here. Now our fifth procedure is saying, now after obtaining potentiometer, we're going to make a subject circuit diagram for each equations here. Okay, so for this equation, we'll come with this circuit diagram, whereby we feed the gains on top of the bubbles, and these factors, we feed it here. Okay, now this is 10y, we feed it here. At the end of the branch, all these factors are fed here. Since this 100 is so huge, to make work easier, we can just decide to put a 10 here and a 10 here. It still means the same thing, so this means that 10 times 10 is 100. Then if we multiply it again by 0.1, it will get us back to our 10 here. It is just the same. So the all of this value is similar to our negative second derivative of x. Now we are going to pass it through an inverter. Now an inverter will bring about an effect of changing the signs. So if it was a negative, it will change to a positive. Okay, now we are interested with an output of x. What should we do to this so that it will, after all, we'll get this output? Now we'll introduce what we call an inverting integrator. It plays a role of integrating. So if this is x, second order of x, it will integrate it to first order of x. Then since it is an integrator, so since it is an inverter, so it will cause a sign change. Okay, now this is positive x, so the result here, we will have an output of negative x as the result. Now for us to get this this output of x, which is our desired value, we will have to pass it through another inverting integrator, whereby this first derivative of x, which is in negative form, it will be integrated to x and it will be inverted to positive. Now we have our desired value. So we can just imagine if we didn't introduce a negative sign. So after all, after doing all these processes, our desired value would have a negative. Okay, that means that we would have used some more inverters, and our circuit will be very long. So to just avoid that, it is very important for us to introduce a negative sign at the equation. Now this diagram is what we call an open loop. An open loop diagram for this equation. So at least we have answered this question halfway. Draw an open loop and a closed loop flow diagram of the analog system. Now this is an open loop diagram for this equation. It plays a role of integrating. So if this is x, second order of x, it will integrate it to first order of x. Then since it is an integrator, so since it is an inverter, so it will cause a sign change. Okay, now this is positive x, so the result here, we will have an output of negative x as the result. Now for us to get this this output of x, which is our desired value, we will have to pass it through another inverting integrator, whereby this first derivative of x, which is in negative form, it will be integrated to x and it will be inverted to positive. Now we have our desired value. So we can just imagine if we didn't introduce a negative sign, So after doing all these processes, our desired value would have a negative. Okay, that means that we would have used some more inverters, and our circuit will be very long. So to just avoid that, it is very important for us to introduce a negative sign at the equation. Now this diagram is what we call an open loop. An open loop diagram for this equation. So at least we have answered this question halfway. Do an open loop and a closed loop flow diagram of the analog system. Now this is an open loop diagram for this equation. Match the now these are the two diagrams. Now these are the two diagrams combined. This is the diagram for equation 1 and the diagram for equation 2. Note that nothing has changed. For example, this being the open loop diagram for equation 1, we have placed everything the way it is. So our gain 0.3, 0.4, 0.1 and 0.2 we have just plotted here the way it is respectively. So it is just the way it was, and this diagram down here, the diagram down here is just similar to this open loop diagram for our second equation, and just see that nothing has changed. 0.5, 0.3, 0.7 and 0.12 we have just plotted it the way it is. Now the only change is that we are going to match every factor here with what corresponds to it at this block diagram. For example, let us start with this one, which has a gain of 0.5, which its factor is 10 first derivative second derivative of x. So where do we have our second derivative of x at the combined block diagram? So here it is, second derivative of x, and the values here should be the values here. Okay, so we are going to loop here like that to that point and put a 10 here, because this value here is also 10. Now we are done with that, and then we are going to proceed to where we have a gain of 0.3, and our factor here is 10 first derivative of y. So where will it be? It will be somewhere here. It will be somewhere here. So we loop this point here, and notice that I've made this bump sign to show that there is no connections at all, and it will take us here. And since this had a factor of 10, we should place here 10. Then there's something you should be very keen to see, that here we have a negative sign, and from where we looped it had a positive sign. So it is not the 2 points will not be equal if we don't introduce this inverter. So by introducing this inverter, now it is represented by this triangle and a bubble here. So the 2 means it has an inverting effect. So our negative 10y first derivative, it will be inverted to positive 10. So it will be the same. The value here will be matching. The value here will be matching. Now let us proceed to our next value, which has a gain of 0.7. Now our 0.7 has a factor of positive 10 first derivative of x. Now where will we get this first derivative of x in the entire diagram? So it is found here. Now we look from this point all the way to this point, and note that this is a positive and this point here is a negative. So we'll introduce a inverter by this triangle, whereby the triangle and the bubble over here will just show us that it is an inverter. So our negative 10 first derivative of x will be inverted to positive 10 by this inverter, and the information here will be true. And finally we'll have this whereby we have a gain of 0.12, which is over here. It will be looped to where we have our y, so it will be looped like that. Here is where we have our y, so since here it is 10, here also should be 10, so that is 10y. Now let us proceed to the other diagram, which is of the second equation of our first equation. Now the gains here 0.3, which has a factor of 10 second derivative of y, will be plotted here. So we'll try to match it with where we have a second derivative of y. So it is here. We look from here all the way to that point. So it is for all this value. And note that this has nowhere to be plotted. It is just 10. So it will simply end here. It will be looped nowhere at all. Just to summarize everything, remember that we've used this sign to represent this circuit, this inverting circuit, whereby here we placed these branches form the summer, and our gains here we saw that it should be less than unity. Now also I've used this sign here with a bar to denote an inverting integrator equivalent to this circuit. Thank you for watching. Don't forget to subscribe.